Okay, so um, this will be our first video to kind of introduce us to polar conic sections and really formalize them. In order to, besides a circle, which we know how to graph polar circles, we want to look at parabolas, ellipses, and hyperbolas. We want to look at them again through the lens of like polar coordinates, because they allow them to be functions. And so we're going to really just start from the basic definition of, how can we define them so that they do stay functions. So each of these polar functions is going to have one directrix and one focus. And that's a little bit different than what we're used to, because ellipses and hyperbolas used to have two foci, and only a parabola had a directrix. But in looking at them through polar functions, the way we're going to define them, actually all three of them are going to have a directrix, and all three of them are only going to have one focus. And the focus, in order for this to be, for these to be functions, that focus we're always going to define as the pole. So the focus is equal to the pole, always. That is horrible that I couldn't write that very well. Let's try that one more time. So the focus equals the pole. Okay. So, and then the directrix is this other line that's not really part of the graph, but it's going to help us fit this inequality, which is going to measure eccentricity. And again, we've heard that word eccentricity. It's just going to be a ratio, and the eccentricity of each conic section will be defined, based on its shape. And so we're going to measure that distance, and we're going to compare it, and that it'll be a constant value for every point that's on that graph. Now, if that constant ratio is equal to 1, our graph is going to form a parabola. If that ratio is less than 1, it's going to form an ellipse. And if that is greater than 1, it'll form a hyperbola. Okay, so we're going to try to recognize, well, where do we see this eccentric value? And it turns out that if you have a function, a polar function, right, that looks like something like what I have here, whether it's form 1, form 2, form 3, or 4. So your goal is to get a 1 in your denominator, and it becomes a sum or a difference of your cosine. If you can isolate that, so there's a sum or a difference for that 1, the eccentric value will be right in front of that coefficient. So I've presented 4 forms, and really the 4 forms really indicate, is it a positive cosine versus a negative cosine, right? Is it a positive sign versus a negative sign? And so that's going to give us the orientation of these conic sections. But if you can isolate the 1, then you know what the eccentric value is. And so we already know what shape we will be getting. Okay, now there's another value up here that's called p, and that distance p will represent the distance to the directrix. So I think I have that up here. Right. So if you can find what that p value is, there it is. Sorry. So if you could find this p value up here. So what ends up happening is that the numerator consists of 2 constants, your eccentric value that you just found times your p-value. And your p-value represents the distance the directrix is away from the pole. So what I'll write down is your p-value. So your p-value is the distance the directrix is from the pole. Now, where do you draw this line, right? Because it's a directrix is a line. So where you draw this line then is determined by your trig function. So if you're negative cosine, you would draw this in the negative x direction in terms of measuring. If you're positive cosine, then you would draw the directrix in a positive x direction. If you are negative sign, then you'd measure the distance in the negative y direction to draw your line. And again, if you're positive sign, you draw it in the positive y direction. So our goal is to really make these into standard form, and we'll know a lot about these conic sections. And so I think best is just to jump in and start graphing, and I'm actually going to go in reverse order. I'm going to start with number 3. And I like number 3 because it already gave me a 1. So that's our goal. And then when we don't have a 1, then we're going to have to look to see, well, what can I do algebraically to make a 1? That's not hard. But I like there's a 1, because once there's a 1 here, I know that whatever coefficient sits there is my eccentricity. In this case, since there's nothing other than the understood 1, my eccentricity is 1. So the fact that my eccentricity is 1 tells me I'm going to be a parabola. Okay. Now, once you know your eccentricity is 1, you also know that your value of 4 is equal to E times P. And we already know that E is the eccentric value. So that means my P value is equal to 4. And that 4 is going to be a distance to get to the directrix. So it's the distance to the directrix. And since it's a negative cosine, I'm going to measure that distance in the negative x direction. So in the negative x direction. Okay. So I already know what I'm looking at. But based on eccentricity, I know it's a parabola. I know how to find my directrix at the end when I want to draw that. And so then I'm going to create a table of values of my 4 quadrantal values. So again, just some key points. I know it's going to be a parabola, but these key points are going to help me really create the scale of this parabola. So we're just going to put in 0, 90, 180, 270 to measure out the radius. So putting in 0 into cosine gives us 1. 1 minus 1 is 0. Uh-oh, it's undefined, right? So it does not exist. So we go to the next point, 90 degrees. Cosine of 90 is 0. 1 minus 0 is 0, so I get a radius of 4. So at 90 degrees, 1, 2, 3, 4. At 90 degrees, I know my R is 4 units. Okay, now let's go to 180. Cosine of 180 is negative 1. So I get 1 minus negative 1, which is 2. 4 over 2, which is 2. So I now know my radius at 180 is 2. So there's 2, 180 degrees. And then when we put in 270, it's going to behave like 90. We're going to get 4 again as my radius. 1, 2, 3, 4. So 1, 2, 3, 4 is here. 4, 270. Now, if you remember at the very start, I had mentioned the pole is always the focus. And I know this is going to be a parabola. So just like the nature of like parabolas we've seen, it sort of has to encompass the pole or the focus. Also, I'm opening towards 0, and that's exactly where I have an undefined value, right? I have no value at 0, so I'm never going to hit positive 0 over the x-axis, right? So I'm just going to draw this parabola. I know it has to open in this direction because it has to really surround the focal point. Now, it is also sort of counterproductive, or not counterproductive, counterintuitive, because you would think, oh, cosine, negative cosine, should this be opening in the negative x direction? And it's actually not. Remember, the negative x direction is where we're going to find the directrix. And that directrix is going to be 4 units back, right? So because it's in the negative direction. So I'm going to count 1, 2, 3, 4, and I'm going to draw the directrix right here. This line and this point here actually represent our givens to really create this parabola, because no matter where you're at on the parabola, let's say you pick this point right there and you measure the distance. The distance to the focus is 2. The distance to the directrix is 2. 2 to 2, that's a ratio of 1. And if you move this up to here And now measure the distance to the pole. That's 4. And you measure this distance here. It's also 4. It's a 1-to-1 ratio. No matter where you put this point and you measure it to the pole and to the directrix, you get a constant ratio of 1. So negative cosine doesn't tell us that it opens to the left. It tells us that the directrix is on the left. That's what that function is going to determine. So, and no matter where you're at on this parabola, you will have a ratio. If you measure the distance to the pole to the directrix, it'll be a 1-to-1 ratio. Okay, great. So now what happens when you don't have a 1? So when you don't have a 1, like in example 2, right? So when you don't have a 1, we need to create a 1 in that position right there. So we're going to basically divide all of this by 8, the numerator and the denominator by 8, or multiply by 1/8 over 1/8. And what we're going to do then is reduce this in a way. Oops, put a red here. So we're going to reduce this so that if I do 1/8 in the top, that's just a 3. 1/8 times 8 is just a 1. 1/8 of 4 is 1/2. So I get 1/2 sine of theta. So as soon as I can establish that 1, that's standard form. So the coefficient that's in front of sine, in this case 1/2, that's my eccentricity. So my eccentricity being 1/2, so my eccentricity is 1/2, that tells me that this is going to be an ellipse. So I know I'm looking at an ellipse, eccentricity is less than 1. And it also tells me that my E times P value is 3. And if I know my eccentricity is 1/2, that tells me my P value, oops, 1/2. So it tells me my P value must be equal to 6, right? That's the only way that I can get 3 for that coefficient. So my P value is 6, and so I'm going to be able to find the directrix, right? My directrix is 6 units, so it's a distance of 6 units to get to the directrix, and I'm going to measure it in the negative y direction. So much like the last example, it doesn't necessarily mean that this ellipse is opening more in the negative y direction. It's going to tell me that's how I'm going to find the directrix. And then just like the last one, we'll just pick our 4 points. So we'll pick r and theta, and we'll pick 0, 90, 180, and 270. So when we put in 0, it doesn't really matter which equation you put in 0. Sometimes it's easy. I think sometimes it's easier to put it in the original equation. So sine of 0 is 0, so we get 24/8, which is a radius of 3. Take 90, put 90 into this equation. Sine of 90 is 1, so I get 8 minus 4, which is 4. So 24 divided by 4 is 6. 180. So the sine of 180 is nothing again. So we get 24/8, which is 3. And then 270, the sine is -1. So we get 8 minus a -4, which actually comes positive. So we get 24/12, which is 2. So I have 4 key points. I know it's an ellipse. So let's plot these points on our graph here. So 3, 0, 1, 2, 3. 1, 2, 3 is here. So there's 3, 0 degrees. 6, 90. 1, 2, 3, 4, 5, 6. Oops. Oh, try this one more time. There we go. 6, 90. And then we go to 3, 180. 1, 2, 3. And then at 270, we're only 2. 1, 2. So I know, again, that one of the focal points, or sorry, the only focal point is going to be the pole, right? That's how we're defining these to be functions. So that's the focal point. And so this ellipse, if you think about symmetry, like in the others, like in the rectangular system, there would have been a focus. If this is like 2 units to get to that point, there would have been like another one right here. But again, we're only creating one focal point for all of our conic sections. So I don't even have to worry about that. And then we open up this ellipse. Now, so if this truly were the other focal point, that means the center of it would have been like right here, right? That's halfway between 6 and 2, right? It's 4 units each. So this sort of is my major axes, which means however big the minor axes would look something like in that direction. In other words, it has to be larger or wider than where that 3 is. So I'm just drawing that out just as kind of like a scale or a perspective. So then we draw this ellipse. That point goes wide there. Goes that point right there. Oops, got a little messy there. Sorry about that. Okay, so there's our ellipse. And again, maybe I'll even go even darker here. So again, so we've got this ellipse here. Notice that the bulk of the ellipse is actually on the positive sign, right? The positive y-axis, not the negative, even though we see there's a the minus sign function there. So why is that? Well, remember, that's going to be the direction to get the directrix, and we're going to be 6 units away. So if I count 6 units away, 1, 2, 3, 4, 5, 6, here's your directrix, right there. I'm 6 units away. So 6 units away, and I think I forgot to write the equation of this, but if I'm a horizontal line that's 6 units away, it would be -6 cosecant of theta, or not y equals, but r equals -6 cosecant of theta. So let's measure a point and see what this ratio, this 1/2 eccentricity, let's see how that plays out here. So let's pick this point right here. You measure its distance to this pole. It's 2. You measure the distance down here is 4. A 2 to 4 ratio, oh, that's 1/2. Let's take this point right here. You measured this distance is 3. You measure this distance down to here is 6. 3 to 6 ratio, oh, that's 1/2. Let's look at this point. Right? From 6 down to the pole, that's a distance of 6. From 6 down to -6, that's a distance of 12. It's a 1 to 2 ratio. So every point on this ellipse has a 1 to 2 ratio if you measure the distance of the pole to the directrix. So there is our ellipse equation right there. I'm sorry, ellipse graph. Let me go back and fill in this vertical line, right? We should have done that in the last example. I did not. So if I fill in the equation of this particular line, it's -4. So it's r equals -4. And since it's a vertical line, we'd say secant of theta. Okay. So we'll do one more, right? We'll go back up to example 1. So let's take a look here. Well, in this case, I already have a 1, which is great. So I already know the eccentricity is 3. So my eccentric value is 3. That tells me I'm a hyperbola. Okay, so I have a hyperbola. My eccentric value is 3. Now, I also have my value of 8. So 8 is equal to this product of E times P. Sorry, I'm trying to erase. And of course, it's not cooperating. There we go. So E times P is equal to 8. E times P is equal to 8. Well, my E value is 3. So I'm going to get 8/3 as the P value. Remember, 8/3 is the distance to get to the directrix. This distance to the directrix. Okay, now, and it's going to be measured in the positive x direction. So we'll just do that at the end. Okay, but we know this is a hyperbola. So let's go ahead and get our 4 quadrantal values, our 0, our 90, our 180, and our 270. And so when we put in our radius of 0, so cosine of 0 is 1, 3 plus 1 is 4, 8/4 is 2. You get a nice value. 90 degrees. So at 90, cosine does nothing, so we're at a value of 8, which I have a feeling is going to be off my page. 180, so the cosine of 180 is -1. So we get 1 minus 3, which is -2. So we get 8/2, which is -4. And then at 270, again, much like 90, we get 8. Okay, so I'm going to build, I'm going to build this hyperbola, at least these 4 values. So at 2, 0 is one of the points. At 890, so 1, 2, 3, 4, 5, 6, 7, almost got it, 8 right there. Now, 180, -4. Remember, 180 is over here, but -4, 1, 2, 3, 4 is actually right there. And then 8, 270. So 1, 2, 3, 4, 5, 6, 7, just off the page. So there's 8, 270. Well, pretend I wrote that there. My pen just is not cooperating. There we go. So here's the thing. We know that just like the last 3 examples, there's only one focal point. It's the pole. And we also know that these branches, if there were 2 focal points, the other one would have been like sitting over there. We know that the branches have to encompass the focal point. So one of my branches is going to have to look something like this. Very, very wide and skinny one. The other one's going to have to look something like this. Right? Because again, the branches have to encompass, the focal point. And if there was another one over here, it'd have to encompass that too. So let's look at this directrix, right? This 8/3. 8/3 is almost 3, right? If it was 9, it would, that would have been a great 8/3, right? But it's almost. So let's see what that, but I guess we can just use green, that's fine. So 8/3. So 1, 2, 3. So almost there. So it's like right here. There's our directrix, 8/3. And it's not wrong, even though visually it looks like it is, right? It's not symmetric. Wouldn't you think the directrix would go right through the middle? Okay, it's not going to, because directrix doesn't have to make it symmetrical. Directrix is the boundary to create this ratio. So r equals 8/3 secant of theta. It's a vertical line. Okay, so let's do some measurements. Let's see if we can get this ratio of 3. So we pick a point. Let's pick this point right here. And we measure this distance to the pole. So that distance is 8/3. So we'll keep track of 8/3. And then we look at so then we look at, oh, sorry. Yeah, no, that's 8/3. And then we look at the point to the pole right here. So that distance right there. Oh, I'm so sorry. You must be watching and listening thinking that, Mr. Brown, you are completely wrong. Let's try that again. This distance here is a distance of 2. So we have a distance of 2, and we're going to compare it to the distance here, which is 2/3. So the ratio of 2 to 2/3 is equal to 3. Fantastic. Let's do another point, right? What if we take the point right here? Well, the distance from here to the pole is 6. And we measure that distance from here to this line that's 8/3 away. So we have 6 compared to 8/3. Well, let's see. 6 divided by 8/3, that's equal to 18. Give me a second here. Oh, I'm sorry. It's not 6 away. This is it's 9 away. Whew. Boy, I'm just I think I'm ready to end this video. Let's try this one more time. This distance here is oh no, that is 8. It is 8 away. And then but I wrote 6, my bad. Let's try 8 divided by 8/3, which is equal to 3. Whew. All right. Well, I know for a fact that this distance here is also 8, and it's 8/3 away, so that gives me a distance of 3. Let me redeem myself and measure this point right here. So this point is 4 units away from the pole. So we have a ratio of 4 compared to, now to get to here, you're 1 1/3 away, or 4/3. So 4 over 4/3. Of course, now it's not writing. 4 over 4/3, which is equal to 3. Okay, so a little bit shaky ending, but the idea here is that to create functions, you must use the pole as your focus. You can find the directrix by looking at the product in the numerator. And then, once again, this positive cosine determines where the directrix is, not necessarily how is it opening.